Okay, so in this video, we're going to take a look at spanning sets, right, which we've talked about before in context of a column vectors, but now we have just a more abstract vector spaces, and as we see, the definition itself remains unchanged in the set here. So in the sense here, let's look at definition in our book SSVS, which is the spanning set for a subspace. Right. Spanning set for a subspace. All right, so it states that a set T spans a subspace W of V, or V itself, right? W could equal V, if every element of W can be written as a linear combination of elements of T. All right, so same idea as before, right? But now we have polynomials, matrices, functions, etc., right? Other more just abstract vectors. Okay, so in other words, what we're looking for is if W is equal to the span of T, then I'm sorry, I lost my train of thought here. If W is equal to the span of T, right, then any vector in W can be written as a linear combination of vectors in T. Since we are looking for set equality, right, one way to prove such a thing happens is we want to show that, right, both of these operations, right? If a vector is in W, then it's in the span of T. If it's in the span of T, then it's in W. Then we've shown equality. All right. So let's take a look at an example. So let's say that we have the set T. So let T be the set defined by the three polynomials. Excuse me. Yeah. 4x cubed all right, and the question I wanna answer is, does T span the vector space of polynomials of degree 4 or less? In other words, P4. Okay, so this is what I'm trying to show. Right? So I want to show is the set T a subset of P4, and is P4 a subset of the span of T. All right, so here, so in order to I find this by doing this. Okay. Now the first one is, the first direction is easy. If we want to say, is the span of T a subset of P4? Well, yes, right away we could say, all right, since P4 is a vector space, closed under addition, I should say vector addition, and scalar multiplication, and T is made up, and T, I'll say, consists of polynomials of degree 4 or less, then all linear combinations are in P4. Okay. All right. So that one is pretty straightforward. Usually will be this direction to show this, the span of T, just because of the nature of the vector space, right? Closed under vector addition and scalar multiplication. So that part is usually not a problem unless the set T starts out with an element that is not part of the vector space that you're dealing with, but that's usually not the case. The tricky part is the next part, right? How do I show that I can write any polynomial in P4, right, the other direction, right? How can I show that any polynomial in P4 can be written is a subset of the span of T? Right, this is a harder problem here. Now, we could say, all right, well, what does a polynomial in P4 look like, right? A polynomial in P4 looks like this, right? Okay. It's some polynomial of degree 4 or less. And again, degree 4 or less, right? So that means that here, these A, B, C, D, and E, these coefficients, right, can be any real numbers, any combination of them, right? That includes 0 as well, right? Some of these may be 0, okay? But in general, it has this form here. So we could say, all right, well, let me start by setting up if I want to show that I can write any polynomial in P4 as a linear combination of T, well, let me start off by writing a linear combination of T. Right, again, linear combination of vectors. Our vectors here just happen to be polynomials. And can I write the polynomial Rx as a linear combination of the vectors in the set T? All right. Okay, now again, we'll group all my, I'll focus on the x's and the powers in grouping like terms. So my first one, I'll have 4 alpha 2 x cubed. The next one I'll have plus alpha 1 minus alpha 2 x squared plus negative alpha 1 plus 5 alpha 2 plus 3 alpha 3 plus 5 alpha 1 plus 2 alpha 3. Okay, equals to R of x. All right. Okay, and then here I can set up by setting equal the coefficients in R with the coefficients on my linear combination, right? So if I do that, I get 0 equals to A, right? 4 alpha 2 equals to B, alpha 1 minus alpha 2 equals to C. And then we have negative alpha 1 plus 5 alpha 2 plus 3 alpha 3 equals to D. And then 5 alpha 1 plus 2 alpha 3 is equal to E. All right, and setting this up, right, the key point here is that the membership in a span always reduces to a question about consistency of a linear system, right? Now, again, boils down to, is this system consistent, right? We could set up here, I'll write this in reverse order here in my matrix just to show what happens in that last column here, right? So 5, 0, 2, right? My augmenting part would be E. Here we get negative 1, 5, 3. That's my D. And then 1, negative 1, 0. That's EDC 0, 4, 0. That equals to B. Right, and lastly 0, 0, 0, A. Okay. All right. And now here we could see that, well, we're going to have a bit of a problem. And maybe in watching this video, as you watch, you're like, oh, this isn't going to work, right? You're telling yourself, there's no way this can work, right? Now, again, right, A, B, C, D, and E, those are arbitrary. Those, if this is in a span, it would work for any possible combination of A, B, C, and D, right? So just keep that in mind, right? These are arbitrary. So I want the system to be consistent for, it doesn't matter what the choices of A, B, C, and D, and E are, right? But we could see here, well, this is not always going to be consistent, right? So let's take a look at, well, let's say if A is 1. All right, remember, it needs to be consistent for any value. So if you can find a value that is not consistent, then you are done there, right? You don't need to go any further. It will not span the set. Because if I let A be 1, what happens is we will wind up with a pivot in the last column of my augmented matrix, and that leaves us with no solution or an inconsistent system. All right, so what that tells me is that P4 is not a subset of T, hence P4 does not equal to the span of T. So T will not span P4, right? And you could have picked up on this, right? If we were looking at the set to begin with, you could see that, oh, there's not enough there, not enough stuff, right? You look at the highest degree, that's cubed, right? And we're talking about the set P4, right? So there's no way you can get any polynomial of degree 4. So right away we could say, all right, this is not going to work, right? Or we could have done this, kind of done it this way and came to the same conclusion here. All right, now the next thing here we want to look at is the vector representation relative to a basis. So let me actually bring up our textbook here. All right. All right, so I'm taking a look here at theorem VRRB, vector representation relative to a basis. And it says suppose that V is a vector space and B is equal to V1 through Vm, right? This is a linearly independent set that spans V, right? So it's a spanning set and linearly independent. So it has those two properties. And it says let W be any vector in V. Then there exist unique scalars such that A1 through A2 to A3 AM, W can be written like this. And that is a unique representation. Okay, let's actually just look at the theorem here to see why this has to be true, right? Just a quick proof here. Whenever a proof strategy here is whenever you're given a theorem that states something is unique, right? The best approach, I should say, to proving this is we'll assume that it's not unique, right? So here, what do we have here, right? We have a set B, V1 through Vm, a subset of a vector space V, right? B is a spanning set. So again, what that means is I can write any vector in V as a linear combination of these, right? B is a spanning set, but it has an additional property, right? B is a spanning set and linearly independent, okay? All right, so it has those two qualities that define it, right? And now I have this vector W, which is in V. Right? Now, if W exists in V, it means that W can be written as a linear combination of the vectors in B. Okay? All right. And now, here, let's say, all right, and then it said this is a unique representation. All right, so that's what the theorem is saying. Let's have a proof. All right, so let's start off again when given this uniqueness theorem says we start off by making the assumption. Suppose there are two representations of W from vectors of B. Okay, so that means not only do I have this, I can also write W like this. Okay, now here let's go ahead and prove that this leads to not necessarily a contradiction, but the fact that A1 must equal to B1, A2 must equal to B2. All right, and again, here we'll approach this using vector space properties and the definition of linear independence. So I can write the zero vector as W plus the additive inverse of W, right? That is the axiom Z, right? Okay, and then from here, let me do some substitution. So we have A1, V1, A sub M, V sub M. And then here we'll have plus, and we'll get minus A1, V1 minus, minus B1. I'll use both of the representations here. V1 minus B, or plus negative B MVM. All right, and then again using vector space properties by moving them, associating them differently, and then doing the distributive property, we get A1 minus B1, V1, plus A2 minus B2, V2, etc., all the way to AM minus B sub M, V sub M. All right. Well, now we go back to our hypothesis here for our set B. We know the set B is linearly independent. So what that tells me again is that the only solution here is the trivial solution. So all these quantities must equal to 0. All right, etc. What that means here is that in order for that to be true, that means that A1 must equal to B1, A2 must equal to B2, etc. A sub M equals to B sub M. All right, so in other words, there is no two representations, right? In other words, that the representation must be unique. Right? Okay, now what that means, one thing that we want to gain from this is that linear independence eliminates any kind of redundancy, and it forces a uniqueness in the representation of the vectors, right? So a spanning set that is not linearly independent gives you infinitely many representations. But a spanning set that is linearly independent will give you a unique representation. All right, and this is going to lead us into our next topic here, where we talk about a basis. Now, a basis has the properties that, one, it is a spanning set, and it is also linearly independent.